Sí, está previsto.
Es muy característico, pero el papel está. ¿Alfo? ¿Nos oye, no? ¿Todo bien? ¿Alfo?
¿Qué tal?
Ah, ¿se oye bien?
Se oye perfectamente.
Vale, vale. ¿Todo bien el viaje? ¿Todo bien?
Claro.
Bien, muy bien. Está también. Bueno, nos vemos, luego hablamos, ¿vale? Ahora ya vamos a empezar.
Okay, let's start the presentation of Daniel number 13 for his work on the post-grade analysis of this color of flows. You have 45 minutes to present your.
So, thanks to the chair of the committee for giving me the floor. First of all, I would like to express that I'm very grateful to you all for taking the time to be here. For those that maybe are connected from home, welcome to this presentation. This is a texture defense. It's entitled Systematic DEM and Constraint Analysis External Flows. This is a work which has been done under the guidance of Raúl Hidalgo, which is present here. And without any more preamble, I would like to show you what is the structure of this presentation. First of all, I would like to give you an introduction about the topic, as well as the motivation that led us to conduct this investigation. Next, I would like to give you an overview about the DEM simulations and constraining method, which are the basis of this investigation. Then I will break the results down in 3 different benchmarks, and finally, I will give you the conclusions of this work. So, we'll start with the introduction by defining what is granular media. Granular media is a collection of macroscopic non-Brownian particles whose interactions occur solely due to friction and contact forces. So, if we examine to a portion of the different scales of the nature, we can see that depending on the particle size, we can have different dominant physics. In this investigation, we will focus on this bond of sizes. In this bond, the particles can interact because of elastoplastic contacts. That means that we will examine materials with these sizes, for example, M&Ms. So why is it important to study granular media? Granular media, the study of granular media is very important because they are involved in a lot of applications in industrial, in the pharmaceutical industry, in the food industry, and mining industry, for example. Moreover, we have that the natural disaster involving granular media, such as avalanches, pyroclastic flows, and landslides. So that's why understanding the behavior of the granular media can prevent the damage that can provoke this kind of natural disaster. So something very interesting about the granular media is that they can act as a different states. They can like a solid, like a liquid, and like a gas. And this macroscopic response is strongly depending on the volume fraction. For example, the volume fraction is defined in the following way: the ratio of the solid volume to the occupied volume. So according to the volume fraction value, it's possible to classify the granular system in two different kinds of systems: dilute system and dense system. That is the topic of this thesis. These dense systems are the more difficult because when we have dense systems, they can behave like a solid or like a liquid, and the liquid is the most difficult macroscopic response that we can see in granular media. So something that is hot topic nowadays is how we can connect the microscopic quantities with the macroscopic response of the granular media. For that, the researchers has been developed some experimental approaches to give us what are the microscopic details of the granular sample. For example, we can take videos, magnetic resonance image, diffusing wave spectroscopy, and X-ray imaging of the granular sample. So then we have identified the center, for example, of these particles. The next goal is try to compare two different images, try to obtain the velocity fields of this granular sample. For example, we have the particle tracking velocimetry and we have the particle image velocimetry. But what happens if we want to know what are the forces that are involved in the system and the contact stress of this system? With normal particles, this is not possible. So for that, we have, for example, photoelastic particles that permit to obtain qualitative insights into the interaction forces, which are extracted after image post-processing. However, we have that these photoelastic particles have a response that is strongly nonlinear, and there is a threshold for detecting small forces. That's why it's very difficult to obtain the quantitative insights of this kind of system. That is before that the numerical approaches covers a great relevance when studying granular media. We can classify the numerical approaches in two different groups. For example, we have the continuum methods, including, for example, particle field element method, computational fluid dynamics, and smooth particle hydrodynamics, that they are very relevant to handle a large granular system that could be very important, for example, in industrial applications. But they need, as an input, sometimes constitute laws. For example, the relationship between the contact stress and the deformation of the material. For that, we can use the discrete methods, such as event-driven and non-smooth discrete element method, which by we can compute accurately the trajectory of the individual particles, and also we can find the forces between them. So what is the goal? The goal is try to connect this microscopic detail with the macroscopic response of the material. So we need a macro transformation to obtain, for example, the dependency of the contact stress with the strain. And how we can do that? For example, the cost-splitting analysis that we use in this investigation is one of the analysis that we can use to tackle this problem. So, what is the general objective of this thesis? So, combining the DEM and the cost-splitting analysis, we can assess the mechanical, or we want to assess the mechanical response of granular samples, addressing the multi-scale nature of granular flows. With this aim, several benchmarks were evaluated. Firstly, the silo flow. Secondly, the fluid penetration in granular bed, and thirdly, the granular segregation due to the shape of the particles. And it's worth to mention that three other work has been evaluated during this PhD. For example, the particle self-diffusion in dense granular flows, the clogging in narrow pipes, and lastly, the granular convection of the granular bed. They have not been included in this presentation neither in the manuscript, because to keep consistency of the general objective with the for keeping consistency of with the general objective. So now I'm gonna show you an overview about DN simulation of the constraining method. So the DN algorithm is based on 5 basic assumptions. For example, the first one is that particles are undeformable. Each particle pair has at most one well-defined contact point, and all particles' interactions are binary. Fourth, we have that each particle's mass and inertia are constant. And as a last assumption, we have that the particles are unbreakable. It doesn't mean that we cannot use, for example, simulations with particles with variable mass. But for this, we have to include another ingredient to the DEN simulations. So, for example, one of the assumptions that I would like to go deeper is in the particles are undeformable, because in reality, when we have particles in the nature, they deform, and the DEN simulations substitute this deformation by an overlapping between the particles. So, depending on this overlapping, we can obtain what is the force between the particles. So, what is the force model that this has been widely used in the literature? We have this force model that we can use to obtain the normal and the tangential force, and it has 2 different contributions. The first one is an elastic one, and the second one is the viscous part of the interaction. So these forces are not conservative. And for the tangential force, we have that they have to obey the Coulomb friction constriction. So we have 2 models which has been employed in this investigation. The first one is the linear spring dashpot model, and the second one is the Hertz-Mindley model. The first one will be used in the third benchmark, and the Hertz-Mindley model was used in the 1 and the 2nd benchmarks. So once we have set the first model, we have to integrate the translational equations and the rotational equation to obtain accurately the trajectories of the individual particles, as well as the rotation dynamics of each particle. So we have employed 2 different codes to do that. The first one is a custom hybrid code that uses GPU, and the second one is the Mercury DPN, which is parallelized with MPI and is developed mainly in the University of Twente. So, what is the constraining analysis? The constraining analysis has been introduced for Isaac Goldrich, and the main goal of the constraining analysis is try to connect the microscopic details with the macroscopic response of the system. So, if we have the system and we have the microscopic characteristic, we can transform these microscopic details in macroscopic field. For example, if we have mass, velocity, and forces, we can obtain the density, the velocity, and the stress tensor here. For that, we need a constraining function. Okay, with this constraining function, has defined a width that is also called like the constraining scale or the resolution scale. So, using this function, we can obtain, for example, the density field, the momentum field, and the stress field. The stress field has 2 different contributions. The first one is related to the forces between the particles, and is called contact stress, and the second one is the kinetic stress, and is related to the velocity fluctuations of the particles in the ground medium with respect to the velocity mean velocity field. So now we'll pass to show you what are the results. So as the first benchmark, we have examined an experimental system that consists with a flat bottom that can rotate at a constant velocity. So in this paper, they found 2 different scenarios. The first one, for small orifices, they found that the volumetric flow rate increases always with the increasing of the rotational speed. However, for larger orifices, they have a completely different scenario where for orifices larger than 4, aspect ratio larger than 4, they obtain a non-trivial, non-monotonic behavior of the macroscopic response, the volumetric flow rate with the rotational speed. So we can see this better in this plot where we have the normalized flow rate against the rotational speed. So here we have that this non-trivial behavior consists in that at the beginning, the volumetric flow rate increases with the increasing of the rotational speed, reaching a minimum here, and then it starts to increase again. So in their paper, they didn't give a reasonable explanation of this non-trivial behavior, since they cannot sit inside of the granular bed. Instead, they only suggested it might be related with a change of the flow pattern based on the visual inspection of the top surface of the granular bed. So in the first case, they say a depression in the top surface, and in the second case, when the rotational speed is applied to the system, they found that the top surface bumped, suggesting that what we have in this case is a mass flow pattern. So for tackle this gap, that we have performed realistic simulations with the same rotational speed and the same system size that was employed in the experiment. Here, I also include the material parameters used to mimic the response of the plastic beads. So from the numerical results, we can plot here the volumetric flow rate against the rotational speed. And we have also included the experimental results for comparison, which are shown through these cruises. So we can see that both the experimental and the numerical results are in a good agreement, and even for the case that this non-monotonic behavior is weak, we can see that they are in perfect agreement, or they are in very good agreement. So from the cost grading analysis, we have shown here what is the velocity field. So each column corresponds to different rotational speed. The first one is when 0 rotational speed is applied, the second row is for 0.3, and the third one corresponds to the case of maximum rotational speed that we have analyzed in this work. In the first row, that means when no rotational speed is applied, we can see the developing of a funnel flow with the material flowing by the center of the granular matter, of the silo. And we can see how the depression develops in the top surface of the granular bed. However, when we apply rotational speed to the system, we can see that this depression is the light, and in another feature that is typical of the flow patterns is, for example, that for funnel flow patterns, we have that the apparition of this standard zone that we can see here and here, for example, that disappears when the rotational shear is applied to the system. Another interesting feature of that is that, for example, the velocity at the top for the case of the funnel flow is more heterogeneous, and it becomes uniform when we apply the rotational shear to the system. So we can conclude from this picture that we have shown that these results, the numerical results, correspond with the experimental ones. So to corroborate the consistency of our results, of our analysis, we have found the momentum just right at the orifice, evidencing a non-monotonic behavior of the momentum with the rotational speed. But we can separate the contributions of the momentum in two different ones. For example, here in the left we have the volume fraction profiles, and here in the right we have the velocity profile. So we know that the density times the velocity profile should be the momentum. So we can see here, for example, that the velocity is barely affected by the rotational shear. However, the volume fraction depends on the rotational speed. That means that the changes in the volumetric flow rate are obeys more to the variation of the volume fraction rather than the variation of the velocity profiles just right at the sum of the orifice. So that means that the rotation speed provokes a dilatancy, a different dilatancy of the system depending on the intensity that we apply to the system. So here we have the kinetic pressure, that is a magnitude that has widely been used to connect the macroscopic response of the granular media with the microscopic response, the microscopic behavior of the granular media. So here we have the kinetic stress for different rotation speed. We cannot tell so much differences from this plot, but if we concentrate in this zone here in the rectangle, which have a height of 1 radius of the orifice and a width of 2 radius of the orifice, we can obtain these profiles. I would like to call your attention to the behavior of the mean kinetic stress as the rotation speed increases. We can see here also a non-monotonic behavior of the mean kinetic stress with the increase of the rotation speed. So that means that the changes in the dilatancy could be related with this non-monotonic behavior, which presents the mean kinetic pressure. And we can see that they are in perfect agreement with the volumetric flow rate that we have shown earlier. Even for the case that this non-monotonic behavior is weak, we have a similar trend of the kinetic pressure. So we have found here a direct connection between the mean kinetic stress, that is a microscopic characteristic, with a macroscopic response of the system. Devices indicating a slight non-monotonic response of the volumetric flow rate with the increasing of the rotation speed. Secondly, we proved that the changes in discharge processes are directly connected to the apparition of distinct flow patterns. Thirdly, a close examination of the velocity and density profiles suggested that the rotational shear impacts the volume fraction more than the particle velocity profiles. And finally, we found that the non-monotonic behavior of the volumetric flow rate is directly related with the similar response of the kinetic pressure. So now I will pass to the second benchmark. As a second benchmark, we have analyzed the intruder penetration into granular media, into granular beds. In this case, the experimental setup consisted in micro radar, which can track accurately the position of the intruder. However, they cannot tell anything about the granular response of the granular bed response when the impact of this intruder. So for that, we have performed realistic simulations with the same system size, exploring the same domain and the same range of velocity of the impact velocity that was used in the experiments. And here I also include the material properties used to mimic the response of the expanded polypropylene beads, which have been used in this case. We can see as something very interesting is that the density of the intruder is far larger than the density of the granular bed. And we have recreated the same volume fraction that was used in the experimental setup with more or less the same number of particles. So here you can see that the evolution of depth of the intruder for several impact velocities here in the same range, both for experiment and simulations, are in perfect agreement. And as it is expected, as the impact velocity increases, we have that the particles get larger in the penetration. Moreover, we have here, now I'm showing you the velocity profile as a function of the depth, of the penetration depth. And they also are in agreement, in an excellent agreement. And in this plot, we have also included the course for applying this phenomenological model that characterizes the forces of the intruder as it penetrates the medium. here we have a first term that is the initial term, and a second term that is the frictional term, and characterizes how the intruder feels more forces as it penetrates the medium. So sometimes the frictional term is written to include the Janssen effect of the granular media. However, from the numerical results, we obtain that the contact pressure have a linear behavior with the depth. Then we can use the linear dependency of the frictional term to perform our analysis. From the systematic study for different impact velocities, we obtain the best fitted parameters using this model. And we have here the viscous constant against the velocity, against the impact velocity, and the frictional constant against the velocity. And we can see that the viscous parameter depends strongly depends on the velocity when the velocities are small. Even though when we increase the velocity, we can say that this parameter doesn't change with the velocity, with the impact velocity. However, for the frictional term, we have here that it barely changes with the increase of the velocity. So we can conclude from this plot that gamma is not a material constant. Something has been shown in a different way depending on the investigation, where some researchers say that gamma should be a material constant. However, we have found that gamma is not a material constant. So to see why is this variation, we will focus on the zero initial velocity and the larger initial velocity, that is 2.323 meters per second. So here, this is a video where we can see, for example, for the, I think that is most interesting here, the video of the kinetic stress, how the intruder provoke disorder in the material, damaging the contact, the contact network that we can find inside the granular media. So here, to the left, we have two panels. The left one is for the velocity, for the initial velocity equals 0, and the right one is for the velocity equals 2.323. And we can see the most important cross-graining field for the different for the penetration of the intruder. The first one is the volume fraction, the second one is the vertical velocity, the third row is the radial velocity, and the fourth one is the kinetic pressure. So we can see here that the volume fraction below the intruder doesn't change depending on the initial impact velocity, but for example, with the vertical velocity, we can see that the initial impact provokes a damage in the granular media, damaging a zone that is later accessed by the intruder. Something that happens in a different way when we analyze the zero impact velocity that barely affects the granular media with the impact of the intruder. So here is to show, to have a better picture that I've said earlier, that the volume fraction doesn't change with the impact velocity. At least they are very, very close between them. So from a theoretical point of view, we can write the conservation equation for the energy, applying a model which has been employed before in a similar system. As a novelty, we have written this equation in terms of the co-moving reference system frame of the intruder. So here we have the evolution of the temperature, and here we can neglect this term because the velocity gradient tensor we have shown in the manuscript that is neglectable. So we can say, here we can identify the convective heat transmission, and here we can identify the collisional granular dissipation term. So if we apply the Fourier law and we insert this equation in the original one, we can obtain this differential equation that describes the evolution of the temperature with the time and with the with the distance between the granular bed to the intruder. So the most simple solution to this equation can be written this way. That is a multiplication of two different factors that are exponentials, and this tau here is the temporal characteristic time, and this here is the characteristic length of the process. So the granular temperature can be assumed to be directly related to the kinetic pressure. So if we plot the kinetic pressure normalized with the value at the surface of the cylinder of the intruder, we can see that all the curves collapse here, denoting an exponential behavior. That means that the process occurs under a slow diffuse convective heat regime, because this in agreement with the thing that we see in this equation here. And the characteristic length is 2/5 of the particle intruder dimension. That this is in agreement with the inertial term that we have proposed for the forces between the intruder and the granular bed. So here we have this slide summarizes the main results that we have found. And here we have firstly that the viscous parameter depends on the path velocity. However, the frictional doesn't change with the path velocity. At least it doesn't. It varies less. It changes less, and we have found that the process occurs in under a slow diffuse convective regime. And the characteristic length that we have found for this process is in total agreement with the initial drag term that we have used in the simulations. However, additionally, we have seen through the cost-bending field that the initial impact provokes a damage in the granular bed, breaking the first network that we can see in this zone, that later is accessed by the intruder. So as a partial conclusion, we can say firstly that the numerical simulations accurately reproduce the experimental results obtained by using a non-invasive microwave radar system. Then the obtained trajectories were in very good agreement with a well-accepted phenomenological model, and we found that the coefficient of the inertial drag was not a material property. Finally, we found that the kinetic pressure profiles in the moving frame of the intruder always decays exponentially with the distance to the intruder, and the characteristical length was practically independent of the initial speed of the intruder, in the order of the intruder size. This is in agreement with the inertial dissipation drag that the intruder experiences. So I will move on to the last benchmark that we have studied in this investigation, and here we address the particle shape segregation in a rotating drum. Segregation takes place whenever a granular material flows, so the particles with different properties, namely density, size, shape, or friction, are prone to separate. So that means that the flow segregates. In our setup, what we have is a rotating drum with a nature inside that is composed by different particles. We have spherical particles and non-spherical particles. So we will analyze in this investigation only shape segregation, because we will keep the volume and the density of this particle to be the same. So here, these are the main details of the experimental setup. So we have take into account the ellipsoid particles as a subset of superquadric particles. So if we have this general equation for the superquadric surface, if we evaluate these exponents at the value of 1, we will obtain ellipsoidal particles. So defining after that the aspect ratio as the ratio between the two of the semi-axis and making the other one equal to see, for example, we can obtain different shapes, different ellipsoidal shapes. And if we set these two formulas here, we can obtain particles with a different shape but keeping the same volume, and the density of the material here is the same. So, depending on the upper ratio value we will have, if the upper ratio is less than 1, we will obtain oblate ellipsoids, and if the upper ratio is larger than 1, we will obtain problate ellipsoids. So this is the system, this are the characteristics of the system, the geometric characteristic, and we have simulated a non-dimensional system. That means that the diameter, the mass, and the gravity of this system is equal 1. We have set as a first model the linear spring transport contact, as I said earlier, and the normal coefficient, and the collision time, and lastly the color coefficient is said to be 0.5. So the number of particles involved in this system are 4,000 particles. So that means that we have the same number of particles with the ellipsoidal shape and 2,000 particles with the spherical shape. And the rotation of this system is set such the prime number is equal to 0.01. That means that in this case we have a system that is in rolling regime. The rolling regime is one of the regime that we can find in the normal media when it's inside a rotating drum, and below this dash line, what we can find is the solid vertical rotation. That means that the normal media here rotate with the rotation of the drum. And above this dash line, we will see the particle flowing in this zone, and that's why the name is the flowing line. So here I'm showing you a video of the simulation, and we can see how the spherical particles suddenly go to the center of the drum, while the oblate particles go to the periphery of this drum, denoting a strong segregation pattern. So at the third rotation, if we analyze the same system but for different upper ratio, we can see that depending on the upper ratio, first the strength of the segregation is different, and secondly we can see a very interesting phenomena, that is that an inversion of the segregation. That means, for example, that for oblate particles, here for 0.1, that is the most extreme case that we have analyzed, the spherical particles are in the center, and when we put the aspect ratio of 0.5, we can see the opposite behavior. The oblate particles are in the center. And the same happens with the problate ellipsoid. Here we have that the elongated particles are in the center, and then when we reach 4.0, we can see that the spherical particles are in the center. So this is a result that was obtained before, but for only a few of the aspect ratios. In this work, we would like to to do a systematic study of the segregation pattern with the varying the aspect ratio systematically. And another thing is to offer you a well-grounded theory that explains what are the causes that are causing this flip in the segregation, that in my opinion is the most interesting thing of this system. So how we can characterize quantitatively the segregation here. If we define the partial volume fraction of the particles, for example here, we can say that this here are the spherical particles, and this is the volume fraction of the total volume fraction. We can obtain these fields here. What we have here is the volume fraction profiles average in the system, and we can see that the same that we saw before for the cases of the snapshots. Here the spherical particles are in the center, then the spherical particles go to the periphery, and here we have the same also. we have that for 2.5, the spherical particles are in the periphery, and for 4.0, the spherical particle goes to the center again. So, how we can characterize this segregation? If we define this mixing local index, we can characterize what is the mixing index for each point. And to obtain the global index, what we have to do is to integrate this local mixing entropy in the for the whole domain, weighted with the density of the granular vector. Then we can rewrite this equation in order to obtain a normalized mixing parameter to keep it between 0 and 1. And as the mixing index and the segregation index are complementary magnitudes, we can define the segregation index in this following way. We will be n minus 1 if the spheres segregate inwards, and it will be 1 minus n if the spheres segregate outwards. So with this parameter, we obtain this profile for the segregation. So this is the segregation against the different aspect ratio, and we can see, for example, for the case of here, we don't have emissions because here is a mixture of sphere with sphere, so we don't expect them here, and we obtain that the segregation is very close to 0. And as the aspect ratio increases, we can obtain that the segregation starts to increase until the maximum, and then we have a non-monetary behavior that decreases the segregation again. And here, close to 3.7, what we have is an inversion of the segregation. And the same happens when we go to the opposite way. If we go to the other particles, we will obtain the same, a maximum of the segregation here, and after that, a flip of the segregation. This minus the blue triangles means that the spherical particles are going to the periphery, and the red circles mean that the spherical particles are going to the core of the drum. So we will apply now the mixture theory, and to apply the mixture theory that said what is the conservation equation for each of the constituents of the mixture, but including this new term that is the inter-constituent force that should be the summatory for all the species should be 0 because the self-news slope. There is a procedure that was realized, was done by Fan and colleagues, and that has based on the idea of the overstress that Gray and Thornton did years ago. So what we have here is the stream velocity. So if we multiply, the idea is that here the segregation should occur in the perpendicular direction to the stream velocity. So what we have to do is to multiply this equation by the normal direction in each point, and we will obtain this balanced equation. And the last ingredient that we have to introduce to this equation is to write it in terms of the partial quantities. If we do that, and we apply the Darcy's law for the interconstituent force, we will obtain the next expression. The next expression is the segregation flux that is depending on two different factors. The first one is the kinetic mechanism. We can see here that depends on the kinetic gradient, and the second one is the gravity mechanism that depends. Here we can see that this prefactor is multiplying the gravity acceleration. So, and another thing, we can see here, if we have particles that are overstressed, contact overstressed, with respect to the volume fraction that the particles are occupying, we will obtain that the particles are overstressed, and we will have a segregation flux. And the same for the case that they are more overstressed due to the contact stress than the kinetic stress. So to show the final results, what we have here is the contribution of the two mechanisms. That is this plot here, and here is the gravity mechanism, and here what we have is the kinetic mechanism. And at the end we have the summation of two of them. And we can see that, for example, for the cases where the spherical particles go to the periphery, what we have is that the gravity mechanism doesn't play a major role in the system. However, when we increase the aspect ratio, we obtain that this gravity mechanism becomes more relevant. And the same happens with the with the Rayleigh particles. For example, here for the kinetic stress that always is present, less that for the first case. We can see, for example, that this point here that is supposed to segregate to the periphery, when we obtain when we sum two factors is that the segregation occurs in the opposite way. So if we compare this sum of the model, this final result of the model with the segregation index as a function of the aspect ratio, we can see that they are in very good agreement and the transitions occur just at the points where the model expected. So as a partial conclusion, we can say that our findings show that in effect the segregation intensity varies non-monotonically as a function of the aspect ratio. And at specific values, the segregation direction changes for both prolate and oblate spheroids. Applying the segregation model, we rationalize the effect of the gravity and kinetic mechanism in the segregation process. The outcomes evidence a competition between both mechanisms. And we found that for moderate aspect ratio, the kinetic mechanism is responsible for the spherical particle segregation to the periphery of the drum, and the gravity mechanism playing only a minor role. Whereas at the extreme values of the aspect ratio, the gravity mechanism notably increases and overtakes its kinetic counterpart. So now it's time to move on to the final conclusions. And here we have as a general conclusion that this thesis has aimed to advance in understanding the mechanical response of granular samples, developing DM and macro averaging strategies. Secondly, the use of containment mechanics formulations has also allowed for the addressing of the multi-scale nature of the granular flows, improving notably the understanding of steam behavior. And finally, specifically, we have examined three different processes: a silo flow, an extruding moving through a granular sample, and the segregation of the granular mixture. So I would like to, prior to give the floor again to the committee, I would like to express my acknowledgement. First of all, I would like to thank to the Asociación Amigos for the funding to the PhD during these 4 years. And as well, I would like to express my acknowledgement to the Fundación Caja Navarra and Obra Social La Caixa for the funding to obtain the international doctor mention, as well as the Mercury Lab and the Mercury DPA, where I did my research stay. Also, I would like to express my most deepest acknowledgement to Raúl. Without him, this work wouldn't have been possible. As well to my family connected from home, for all the colleagues of the department and the granular lab team, thank you for accompanying me this journey of 4 years. Of course, to the PhD colleagues that I have, thank you. Thank you also to Satoko for supporting me and for being so patient with me. That's all. I would like to give the floor to the committee.
Thank you very much. No, questions. First of all, I have no question. Okay, you can ask this question.
Okay, first of all, let me congratulate you, Dariel, and Professor Raúl, for what I think is an amazing work. And the first thing I wanted to stress is something that you have already mentioned there. It's not pretty mentioned here in the manuscript, which is that I think it's a record for this department that you have worked in 6 different scenarios, 6 different problems. Okay, all within granular media, but I think it's amazing that you have been able to work within all these 6 problems that you mentioned there. Not because of the problems themselves, but also because you need to deal with some of the most important challenges in the field of granular media, like, for example, working with particle shape, working with extremely confined scenarios like in the glowing narrow pipes, which is also a hot topic in thermal media today, with particle wall interactions dominate the dynamics. Also, you have to implement boundaries that rotate, for example, which is also some tricky thing to do numerically, I think. Analyzing characterizing segregation is not really a thing as well. Working with diffusion, etc. Right? Apart from the more technical things like the simulations themselves and the discourse grading, which is interesting from a point of view, is a technical thing. So I think that after this, you get a broad scope of what thermal media is, and gives you a very solid background of this field. Okay, having said that, this is a good point, but also has an important drawback from my point of view, which is that you feel that there is a sort of lack of depth in the analysis of some of the problems. When you listen to the presentation or when you read the manuscript, you feel that you will need more. I mean, I feel that I would like to have more information, I would like to have more discussion about some of the results, of the connection among different results, of the connection among the different fields. So I know this is more a recommendation for PhD supervisor than for you. I think that, okay, perhaps in other fields, this is something that is more common. As Anthony says, in applied mathematics, you have a technique and you apply it to different topics. So I agree, but as for this department, it's not the most standard thing. I think that if you focus as a whole in your PhD, a couple of topics or 3, but 6, I think it's a lot. Sometimes you realize that it's impossible even to have one support to learn about all these models that are behind this every single program. I think it's difficult. So what I miss is sometimes the extension of results, and also in the writing you realize this. For example, for me there is a clear example. In chapter 4 you write as an appendix. And you plot, and you present some plots, but I think they are not an appendix. I mean, they should be in the discussion of the results. I guess that you put them as an appendix because they were not as an appendix in the paper, or because they were obtained afterwards, or something. But they are an important part of the discussion of the results. So this is my feeling about the PhD, the problem that this has. So after commenting this, my general view, let me just go into some specific points. And starting by the first part, well, I have to say that I enjoy a lot the second chapter, because it is something that I learned. I think it's good. For me, it was very good. In opposite to what it was mentioned, the weakness that I was mentioning, because this is a general chapter that I think is good. So in the third chapter, in 33, there was also a plot that you showed there, which is in page 23 there. You mentioned, I think it's wrongly explained in the manuscript, because you say that it's monotonic, and I guess you meant non-monotonic. If you go to your presentation, page 23. Your presentation is page 23.
Yes. Okay.
We cannot see it. No. So then it's yeah, this one.
This one?
Yeah, this one. So you mentioned in the manuscript, I think it's wrong. You mentioned that in the P is monotonic and it's not monotonic. Right?
I say that? Sorry?
In the manuscript you say it is monotonic.
It's not monotonic. No monotonic.
In the manuscript it says monotonic. So this is very confusing because when you are reading the manuscript you get lost, and also you say that okay, then it is not monotonic here. But then you say that the packing fraction is also not monotonic. And for me, okay, in the center perhaps it's clear that it's not monotonic, but come on, the green and the blue.
Yes.
It's difficult to say that green and blue are different. I mean, for me, it's difficult to say that they are different in the, because what are you computing? In the center, yes, but what are you computing? The average or the integration or so?
Can I expand on this?
Yes. This is what I want to.
So, as you can see here, when no rotation is applied to the system, we have that the maximum velocity.
Okay.
So, the thing happens when we apply rotation to the system. Here we have that the difference in the velocities are not so greater.
Yeah.
But here, I would like to focus only when the system is submitted to rotational shear.
Okay.
So in this case, we have, for example, 0.3, 1.0. So here we can see that for 1.0, the profile is larger,
Okay.
always like this one.
Yeah.
So what I say is that the rotational shear doesn't affect a lot the velocity. I mean, between the different rotational speed. But it affects more the volume fraction depending on it depends on the
Okay.
rotation velocity.
But in the rotating experiment.
In the rotating segment.
Okay, good. So perhaps the answer to the next question is the same. That in figure 3, well, all the next figures that you compare different.
Yeah.
For example, this one.
Yeah.
Why do you normalize? Well, I realize that you normalize by 1 hertz.
Yes, that's right.
Why did you normalize with 1 hertz? I mean, what we know is the static side. So that, for me, that's the reference, which is what the 99% of the works have been done. So why do you normalize with 1 hertz?
And basically, it's because we based on the previous work that was experimental one, and they normalized the values
With 1 hertz.
with one word.
That's
With one.
one.
Yes, and that's why we use the same reference to compare to
Okay.
results, both.
Okay. For me, it's just, well, it's something that you will have expected a bit more discussion about why do you normalize with 1 hertz, why do you, I mean,
Yeah, basically, I agree with you that maybe the static situation should be the reference, but it was because to keep the consistency with the experimental results.
Okay. So next one is in the next chapter.
Is
So
here,
in figures 4.3 and 4.4, which are the ones where you very nicely reproduce numerically the intruder penetration, or this one.
Yeah.
So you say with minus beta, you also say here that there is an excellent agreement.
now,
And I agree with you that there is an excellent agreement, but I think that it's better if you, as you did in the previous chapter, you plot the numerical simulations on top of the experimental results, as you did in the first experiment. Why you didn't do that, or
yeah, because I should say that, as you can see here, the velocities are not exactly the same. We have here, for example, this one is 0.40, and here the closest to this one would be 0.98. And the differences are because in to obtain this impact velocity in the numerical setup, we have to spend the time to obtain what is the impact velocity. Because if we release the particle from a different height, we will obtain a different impact velocity in this case. So this
is a number that you measure after the simulation, and it's not something that you control.
Yeah, I can control it in the simulation because I can put it exactly on the top of the cylinder, but in the experiment this is not possible. You have to put in a different height.
So experiments were after the simulation?
It was simultaneously. The work was done simultaneously.
Okay. So there is a final question on this field, that is figure 4.6 in the manuscript. That is again, for me, 4.6.
Is here in the presentation?
No, I don't think so. Anyway, don't worry. So the point is that the forces, you show that in the simulation, the forces fall below the weight. The forces that the medium make on the intruder at the end of the penetration fall below the weight of the intruder.
Yeah.
And this is strange because I realized there and in the next slide that the intruder stops. I mean, in the simulation, the intruder stops, and you mentioned that the forces fall below the weight. So I understand that the problem of this plot is the rescaling with the Tn, because you rescale 4.6 figure. You rescale by Tn. So what you see there is kind of strange because you are rescaling with Tn. And this is another of my concerns. I think that you go fast over the manuscript, presenting figures where you first present things that are rescaled before presenting the raw data. It is like reading manuscripts instead of reading a PhD manuscript. But my question is, how do you explain this? How do you explain that the force fall below the weight and the intruder stops the penetration?
So first of all, I accept the critic of this about this, but I think that this because the lecture of the TN is wrongly elected because we didn't expect or we didn't wait enough time to see that the particles are in rest.
Okay. So it's the action of TN.
Yes, I think that is the problem.
Okay. So I have more questions about the third chapter, the last chapter that I enjoy a lot, and I think it's a very interesting work, but I think I'm running out of time, and Anthony is more expert than me in this topic. I'm not going to ask about it. Really?
Sorry. Okay, so my first question, which given where we are, I'll ask is on slide 27. If you can go back one slide. So a topic you never discussed, and I don't know how you did it, is how do you calibrate the DM models? Because your agreement is very good, but you never mentioned how you get the parameters. So how do you do it?
So I don't know, we have not do like a fitting of the parameter. We have selected the parameter from the literature to reproduce the behavior of these polypropylene bits. But I have to say that the parameters that is more important in this simulation is the density of the particles. In this case, the differences between them can provoke a different response to the granular. And we have also the hardness of the particle. It's here. This is the most important, the most relevant parameter at the time to study this kind of system.
So the related question then, you picked the Hertz-Minimum model. Why did you pick the Hertz-Minimum model? And in the last chapter, you picked the extreme data. I was curious what motivates to choose a force.
Yeah, I have to say that the expanded polypropylene particles are very soft. And when we have particles that are very soft, the Hertz-Minimum model works better than the linear transport model. That's why I use this case. When the particle is harder, it doesn't care so much. But in this case, it cares.
So thank you very much for that. So then maybe you actually expressed my follow-up question. Yes? So in the very beginning, you actually said, well, in your opinion, the granular materials are in gases, liquids, and solids. In your opinion, liquids are the most difficult to study.
Yes.
Why?
Yes, because when we have the liquid state in the granular matter, depending on the external shear and other parameters, as the material properties, we have to connect the contact stress, for example, with the deformation of the material. And this is, for liquids, I think that this is the most challenging topic in granular media. Try to connect the microscopic response with the macroscopic, the microscopic detail with the macroscopic response of the system. That's why we need DN simulation to find it numerically.
Okay. I was arguing it the other way. So I said, well, the liquid models, continuum models of liquids came first and gave the best agreement. So I was considered, I like that. So I'm not disagreeing. Okay, so can we talk about the course grading chapter 2? Because I don't think so just start at the beginning. At the bottom of page 9 in the pieces, And I'm just curious if we do any other. You make a statement about choosing the path. So when you do the best, you have a path.
Okay.
Yep.
Let me make this.
Yeah.
Okay, see, I was looking for. Okay. Page number 9.
I think it's page number 9, just above,
Okay.
the last section, 2.22. The last sentence, sorry.
The last sentence?
Yeah.
Here.
Page number 10, yeah.
Oh, let me see, I have to.
But the people say that they need it. Sorry.
Okay.
Yeah, so it's in the last sentence, this section, the paragraph, and I also scroll down, your page is slightly different. Yeah. That is the scroll page from. Yeah, you describe the pattern of arbitrary for the stress. So you said, so when you do the stresses, you have a path interval. And you say here it's arbitrary, okay? Yeah. So if you take a different path, what would the answer change? And what consequences would this have for your model?
So we are thinking about for the contact stress.
Yeah, you're talking about the contact. You talk about the contact stress and the kinetic stress. You said there's a path interval in here, and you said the path is arbitrary. So I'm just curious what would happen if you took a different path. It's arbitrary.
Okay, this is an interesting question. I guess that, for example, in the last case that we have analyzed in the thesis, we have employed, it's not a different path, but we have employed that the path is from the center of the particle to the contact point, and we obtain the different contributions from this. So we obtain that, in this case, we will obtain that the total contact stress in this case is the contribution of the separate contribution for the different particles. So I don't have a clear, I think, response answer about that. But Goldrich said that prove this arbitrary path by mechanical principles in the paper. So in this paper. So I really don't have a clear question about this.
The topic you
Thank you for the question.
No,
second.
so the other point you did discuss when talking about course grading is you did discuss how you change your course grading with W.
Yeah.
So how did you choose the course grading with W?
So yes, for example, I saw that from the Weinhardt papers, he systematically studied what is the best cost grading width that we have to take to perform the cost grading analysis. But in our case, we have been taking the cost grading width in the particle scale. We have the subparticle scale and we have the particle scale, so we have only picked one up that is in the particle scale. So we haven't performed a systematic study of what is the best width that we have to take for the cost grading analysis.
So somewhere you compare the different cost grading functions and then figure follow on from this problem. Somewhere because you go to Lucy and Gaussian. Page 20. So you yeah. So in different points in the thesis, you use Gaussian and you use Lucy polynomials. Yeah.
Yes.
And then when you plot them on this figure, they look very different in their shape.
Yes.
Correct. So my question is, if you were to course grade with the same W and swap from the Lucy to the Gaussian, would you get the same results? What I'm asking is, in the way you presented it, is the W the same for the Lucy polynomials and the Gaussian?
So when I did this plot, I put the same width for both of them, but I see that the problem here is that I'm plotting a stability function because I'm doing with these functions are normalized in 3D, and I plotted them in 2 dimensions, or even in 1 dimension. So that's why I did the different scales.
Well, okay, so following on from that, how does the W define for the loose? Maybe it's
It's in there is here. Yeah, it's defined as C should be 2 omegas.
and for the heavy side, W is the full.
The heavy side is omega. Yeah, maybe I have. Maybe the cost gradient function have like 2 times the Lucy one. Yeah, I have to. Maybe I have to fix that.
Yeah, you have to be careful. I think you keep it like that. I think the interpretation of your W in the different course gradient is different. You should keep the same percentage of the function inside the W. Unfortunately, the way Thomas wrote it in his paper doesn't naturally follow that way.
Yeah.
So I think you.
I noticed in the paper that the question is wrongly written in the original paper. So
Yeah, so
I missed something there.
okay, so for the heavy side, is your W the full width or is your W rescale? So for the heavy side, how do you define W? Is it the actual? So just pull out the thing of the heavy side function.
Yeah, for the heavy side, I put the W equals, in this case, is equal 1.
So do you see the problem with this now? Because for the density, the W is one standard deviation. So the amount of the cost range function you have in the range W depends on the function range.
Yes, I think that here I'm taking omega that is less than 1. Maybe I put here 0.5, I think, for the Lucy function.
Okay, yeah, so yeah, it's not your mistake, but just be careful when you compare different functions, what you don't, because the way the W is written, it means something different than each of the functions you can't compare. Yeah, my favorite question. So when you do the cost gradient, it naturally falls out that the stress contribution has 2 components, kinetic and contact stress. Can you give a physical interpretation of those 2 different contributions, or is it just a mathematically niceness? Can you physically interpret the 2 terms separately?
Yeah, I think that, for example, the contact part of the stress is related to the forces between the particles. The negative part is because the velocity fluctuation. So when we have more velocity fluctuations, we have more interactions between the particles. So the kinetic stress have this interpretation. When we have particles that are agitating the particles, we will have that the particles have a larger rate of collisions between them.
So let's be careful here. So if I take a thought experiment, I have 2 particles in a box vibrating next to each other, and they never touch. Do I have a kinetic stress according to your formulas?
Yeah, that's right.
Yeah, so so it cannot be rapidly fluctuating contact because you can get a kinetic stress. I have just a question I don't know the answer to. I may ask you to look at the subsets.
Okay, so I was thinking only intense flows.
Yeah.
Yeah, it's the problem.
But even in that flow, every time you get the contact, it's going to contribute to the contact stress. So even though I agree with what you're saying, physically there's a subtle component to this because every time the contact happens, it contributes to contact stress as well. So the rapidly fluctuating particles be, there's a subtleness to this interpretation.
Yeah.
Okay, thank you. So, as I said, I was very interested. Do I have time for yes, one more quick question? Yeah, okay. So then, given no one is asked, I will ask a question about the circulation on that. Just a very quick question at the end. So at the end, you state what the model is designed for the continuous avalanche regime. And you say, well, you probably won't work in the volume regime. So what would you expect to change if you spin the drum? If you spin the drum at a higher RPM, would you expect the model to work or not? And if so, what should you change?
If I change the regime, for example, but moving from falling to the cascading, for example.
Yeah.
So I suppose if we can avoid the gas state, maybe we can apply this theory. But whenever we have this gas state, I think that it won't be possible to use this mixture theory, because the mixture theory is based on continuity equations. So in this case, I think that we have to apply another thing to solve to explain what is happening in the system.
And what would you apply to your system?
And I suppose that I have to apply the kinetic theory of the cases applied for granular media. So, but to be honest, I haven't seen any like that. The segregation of cases applying kinetic theory. And maybe you are aware about it.
Okay, yeah, I was curious of your opinion. And very quickly at the end, you mentioned I've never said this word, stereosymmeters. Would you expect anything to change if you change from ellipses to the stereosymmeters? Thank you.
I think that we will have also shape segregation in this case, but I think in this case maybe the face-to-face collision we can have like a more impact in the behavior of the system.
So would you expect the model to not work, or would you expect a shift in the curves? So the kinetic stress as a function of the aspect ratio, would that change? Or would the model completely stop working, or would the curves just shift as a function of that?
Yeah, I expect that the segregation strength increases more in the case of for the same aspect ratios. I expect that for the first cylinder to have a larger strength of the kinetic mechanism in this case.
Thank you.
Okay, now it's time for Alpo. I don't believe that you are there, please answer us.
Yeah, I'm here. Do you hear me?
Yes. Yes, I can hear you.
Okay. Can you hear me? Yeah. Okay. Firstly, I would like to congratulate you, and as a second neighbor to Raul, because of this huge work you have done. I had the pleasure to be your reviewer of the first version of the thesis, and I have to say that I enjoyed it very much, and I see that you have made changes to improve it. The thesis is very wide in scopes and deals with so many different situations that I think it could be a methodological tool for grammar matter in theoretical analysis. We are having problems now to explain a problem we have in 3D, and I feel that one of our students will contact you to ask for help, because I see that you have developed these tools. I'm very glad with the thesis from the methodological and from the physical point of view. It has a lot of mathematics, but it's a lot of mathematics in order to understand the physics. So I will not take more time, but I will have one comment. And it's related with the slide number 39 in your presentation, which is where you put the different variation states you find for different aspect ratios.
Could you say again where is the slide?
39.
39. Yes.
Okay, here you can see that for different aspect ratios, you find so many different situations. It's incredible. But now, when you go to the figure 5.8 of the page 73 of the manuscript, which you didn't present, you find the special ratings.
Okay.
Okay, the other one, you're right here. And you see special huge differences.
Yes.
The same distribution of this special ratings give rise to so many different situations in the segregation. And I have a doubt that it could be something done, but how could it be? Do you have an idea?
Yeah, I think that as you know, let me good for the function. We have that this parameter depends of the gradient of the kinetic stress, but it depends also of the on this prefactor. That is the difference between the overstress of the particle, the contact overstress, and the kinetic overstress. So what is changing in the system is this parameter, because I think that the rotation of the drum is provoking more or less the same kinetic value. But what is happening inside the picture is that these two parameters are changing, and that's why when we have particles with a larger aspect ratio, we have that this magnitude increase a lot, and that's why we have these kinetic flux.
Okay, thank you very much. I don't have further questions. I'm glad with what I read and what I heard. So please continue.
Thank you for the question.
Thank you all.
Okay, good. So, Dariel, first of all, congratulations for the work, the presentation. I think it was a very work you have done, and also the presentation was very clear. I would say that I think you are here to defend your work and your thesis, so we have to stick the needle to any specific details or anything. So I have some questions that I think you will answer. So most of the questions that I prepared, unfortunately, they have some overlap with my previous speaker, but I would like you to elaborate a little bit more on some specific details. So first thing is regarding the calibration of the parameter in DEM. One of the things that probably I missed in the thesis were a little more detail on the methodological development. So you explained very well in the chapter 2 how you project microscopic properties on microscopic field averaging. That was very nicely done. The details of the forces, the details of the parameters. There was just a short section where you list this Kn, Kt, gamma n, gamma t, you give a little model, you mention this restitution coefficients. Then you provide number in different applications, and you have very nice results. So I understand that from the previous questions, these parameters were chosen directly from the literature. So that means that there was no fine tuning in your solution. So you pick up the parameter from the literature, and you get magically basic match with the results. Or there were some parameters that you had to tune. So that's my first question.
Yeah, and the reality is that we have tested different parameters, but depending on the system, there are parameters that are more important than the others. For example, as I said before, in the intruder penetration, the most important there is the hardness of the particles. And for example, for the case of the silo rotation, that the bottom rotates, the most important parameter is the column friction parameter. So in this case, the results are highly dependent on what is the column friction coefficient that we put there. So, but the other parameters are selected from to mimic the same behavior of the plastic bits in this case.
How do you know what's the important parameter in particular situation?
No, testing. So if we perform the simulation with a different color friction, we can see that the results are sensible to these factors. But if we change, for example, the hardness of the particles in the case of the rotation zero, the bottom is rotating, we don't detect any changes in the results.
Yeah, no, it's so therefore there is just few parameters which are relevant and that you tune to get, for example, you match with the membrane flow rates.
Yeah,
How do you know that these parameters which you have matched, or you did parametric study to find this value, is connected really to the real hardness of the membrane and then the, let's say, the rheological or the fluid mechanical properties of this sample? with this parameter that you in that specific situation really match the mechanical properties. And what you will do to be sure that this is the case.
Yeah, I agree. I think that this is one of the weaknesses of VBN simulation, that we have a space of parameters, and we can have different parameters that can fit the macroscopic behavior of the system. So if we want to, that's why to know the connection between the microscopic details with the macroscopic response becomes relevant, because we can have the same macroscopic response, but with different microscopic details. For example, it's like we have a function going from the microscopic details to the macroscopic response, and there are several parameters that can go from one point to another one. So it's a weakness of the parameter. Even nowadays, the people that are simulating with DN use, for example, machine learning to fit correctly, or to obtain the best parameter that fit an experimental situation, but it's the same problem. At the end, we have that we can change two parameters and obtain the same result. So I think that this is one of the weaknesses of DN simulation.
One of the cases that in rheology, for example, is just to provide very simple deformation, shear, extension, etc. Extract the discriminating property, viscosity, normal stresses as a function of shear rates, extension rates, etc., and compare your model with this. I don't know if you have ever considered to characterize rheological. So the non-Newtonian viscosity or other discriminating properties.
Yeah, I agree, but as we can see in the experimental approaches that we have shown in this case, they don't have the facilities to do that, for example. So they cannot see inside the granular bed. The only way that we can treat the experimental results is testing with different parameters. Yeah, so yes, but I agree that the best thing is going in the opposite direction, trying to get the connection between the macroscopic and macroscopic relationship, going from the experiments to the DN simulation is also another way.
Okay. So the other question is on the coarse graining analysis. This is you say the link between micro and macro is a coarse graining analysis, because you project to say information from macro to macro. You're not really exploiting to say that information to do a dynamics of the coarse graining. This is not coarse graining dynamics, it's a coarse graining analysis. So you project this information and then you interpret a posteriori. It's a post processing.
Yes, here is a post processing, but there are some work where you can apply the results of the coarse graining to perform hybrid simulations between continuum and discrete element method, and we can use both of them. So, for example, we can obtain firstly the DN simulation, and from the DN simulation obtain the macroscopic field to simulate it continuously, and then we can save time computation doing that, for example.
Okay, so I was more interested in this kind of granular system that you have when you project into a macroscopic model. If you will project into a continuum model, if you will choose one continuum model that has some essential features that you believe are important for your macroscopic system, what kind of model you will choose to describe this system at a continuum level?
Yeah.
What are the essential features? What is a thinning, a thickening? I don't know. Can you have a comment on this?
Yeah. In granular media, we have the continuum models that, for example, they are based on basically on the continuity equations, but including, for example, the term that includes the collision between the granular media. So I will employ one of these one of these models that you can use for in continuum mechanics.
For example, in the first test that you have done, where you mentioned the transition from the, how you call it, from one flow to mass flow, the first one, actually, you can really see that there were stagnation zones, and then it's full flow there. So it's clearly plastic or yield, some yield stress. So I'm just wondering, is a simple yield stress plastic flow like a special model will be enough, for example, to describe this system at a material level, or there will be some additional physics that will need to be?
Yeah, the problem in this case,
Your opinion, it's just
yeah, in my opinion, in this case, sorry, thank you for the question. In my opinion, in this case, we have the standard zone that is in solid state, and we have the another zone that is flowing by the center of the silo that is in a liquid state. So the most difficult thing there, I think, that is the boundaries between the standard zone and the fluid part of the silo. So yes, we have, in this case, depending on the material and depending on the, for example, the external forces that we are applying to the system, I think that the macroscopic response can change a lot depending on of this parameter. So I think that there is not an universal theory that can explain that, but we can obtain insights applying, for example, cost-grading methods. But in this case, I think that we need two different theories to explain what is happening in the standard zone and what is happening in the flow part of the cycle. So,
okay. So may I, last question? Okay, sorry, I was curious because again, I'm not coming from these elements, but I do other things. I was some interest, some curiosity when I went through the chapters, and one of the things that I was also previously discussed was this arbitrarity that you have in this estimate of this tensor Fourier being equal to the function of stress. And this is related, so the kinetic part of the stress is related to the way in which you define the filtration, whether it is in the center of mass of the cell, where you do the coarse grading, or if you define it on the particle position, and then there are this correction, which introduce the local radius to correct. So my question is, can this arbitrate? Because in the end, there is the kinetic stress plus something plus an error. Something that is defined, I don't know exactly the theory behind it, and sometimes it works. I think in the cases you mentioned that this error varies with some parameters, so it's not well defined. So my question is there any way where you can fix, so to say, your protocol, your irreducible stress determination, by a reference value of the stress that you can compute independently in your simulation? Because I coming from the reality itself. I mean, one of the things you can do, you can submit your sample to a shared information and then measure forces on the wall and extract a real value of the stress, which incorporate all components. You are not going to split anything. So therefore, I'm just wondering whether to look at this error in terms of a reference stress component.
yeah, as you can see, it's
What is your opinion on this error on this piece?
from the cost-splitting analysis, one of the most important fields that we can connect, for example, the micromechanical detail to the macroscopic response is, in this case, the kinetic stress. So that's why we employ a lot, because they are directly connected, for example, with the latency of the system, as we saw in the first case. But for example, with the velocity problem, we cannot obtain this velocity fluctuation. For example, if we look at it from the macroscopic way, the macroscopic response, and if we miss these insights of the material, we can lose some of the connections that we can tell about the microscopic details when we transform this macroscopic detail to the macroscopic response of the material. So if we know, I think that in this case, if we know the shear rate of the normal medium, we can set directly what is the kinetic stress that we will obtain at the end. Because this additional term depends on the gradient of the velocity mainly. So I think that we have to, if we can obtain something from the rhetorical point of view, we have to obtain this, the shear rate of the system.
Okay, and very last, so you always use a constant friction coefficient here on the
Yes.
I think there are some evidence. I think the friction coefficient might not be necessarily constant in many cases. So how would you move towards systems where friction coefficient is not constant? If you have any idea?
I know we can implement like a Coulomb friction coefficient, whatever is the property. For example, if we can set that the Coulomb coefficient depends on the velocity of the particle, we can implement it in the but normally when we are studying general media, the general media are hard enough to not taking into account this kind of variation of the Coulomb friction coefficient. But yes, the way if we have like a phenomenological expression for the Coulomb friction coefficient, we can implement it as an additional ingredient to the algorithm.
Okay, very shortly because I think we have already been talking for more time than the candidate, so I'm just going to say 3 things. First, I love the fact that your simulations agree with experiments. I mean, there's something which is a nice step forward for simulations. Years ago, it was not easy to find people who have. Years ago, it was not easy to find people who have even quantitative agreement. Now I see that there are quantitative agreement in many difficult situations. And this is very nice. I think that is, I mean, I'm surprised to see those results, and I think that is very interesting. Second, there's something that I have not liked, but also already been said, that I have a little bit more of a discussion on the methods, the results, and so on. I think that the thesis is at least a little bit short in this sense. For instance, how do you obtain it? I'm going to ask you the coefficient or the parameters of the contact of the model, the usual contacts, and so on. I would like to have also found some explanation of your results. I have only one question, that's on the questions that I should have asked. Why is there a minimum in the flow as a function of a frequency? So we have the rotations in the cell with rotating base. You have access to a lot of variables. Why is there a minimum? Do you have any idea about that?
Yes, and we suggest from the cost-bearing fields that firstly we saw that the dilatancy of the system changes with the rotation of the bottom of the cycle. And this dilatancy is directly connected with the changes in the mean kinetic pressure in the region of the orifice. So what we suggested is that this non-trivial monotonic behavior of the kinetic stress is the micro scale characteristic of behavior that is reflecting in the macroscopic response of the volume fraction. So we think that because we have, for example, less collisions for 0.3 more or less in the rotational speed, we are obtaining that the dilatancy is less, and we are obtaining as a result that the macroscopic response of the volumetric rate has a minimum there as well.
But this is not explained in the thesis, is it? Is this explained in the manuscript?
I suppose that, but I explained that in the presentation, isn't it?
Okay, I have not paid attention to this. But I would have expected some more explanations about this. But your answer is, I mean, it makes sense. And I'm satisfied.
Okay.
Okay. Is there anybody who's a doctor in the room who wants to ask any question? Okay, so we will start the meeting to assess this.
Okay.